Hello everyone. Today I'll be presenting our ECCV 2024 paper titled Xformer, Unifying Contrastive and Reconstruction Learning for MLLMs. This work was done in collaboration with Amazon. The goal of the paper is to enhance the visual representation for MLLMs. For this, we propose Xformer, which is a lightweight transformer module that leverages the complementary strengths of contrastive learning that captures semantically enriched low frequency representations and masked image modeling that captures high frequency and detailed visual representations. Now let's briefly look into the motivation for our approach. Typically, MLLMs employ CLIP-ViT encoder as the visual backbone. However, CLIP focuses on global alignment between image and text, while it lacks at fine-grained alignment or poor visual grounding, as shown in the example below from the CPR 2023 paper, where they show the patch level alignment between the text and the image patches is not very accurate, leading to poor visual grounding. Further, it has also been studied that the self-attentions of contrastive learning capture global information. For example, given an image and two separate query tokens positioned at different parts of the image, the self-attentions of contrastive learning seem to focus on the global information, which is the object in the image, irrespective of the which query token you select, while the self-attentions of MIM mainly focus on the local areas and similar tokens as shown here. So for the query 1, we see the self-attentions are localized to that region, and similarly we find the same pattern for query 2 as well. We aim to leverage the benefits of both contrastive learning and masked image modeling. But the next challenge that derives is how do we combine these two representations that are complementary to each other? First, we start with simple combinations of CLIP and MAE-ViT. Here we depict the architecture of Qformer, which takes in a set of learned queries Z along with the input text and the CLIP features. As shown, at every alternate layer, they have a cross attention with the CLIP features sandwiched between the self attention and feed forward layer to learn enriched representation Z prime. So in order to combine CLIP with MAE, the simple first approach we try is concatenation, where we first align the embedding space of MAE with CLIP using a simple fully connected layer, and then concatenate the MAE and CLIP features, which is then passed to the cross attention layer, along with the learned queries and input as in the Qformer. Note that compared to vanilla Qformer in concatenation, the only difference is instead of passing only CLIP features, now you pass a concatenation of MAE and CLIP features as the input to the Qformer to learn the enriched representation Z prime. And we show that for concatenation, the performance on various VQA tasks. On VQA V2, we find the performance slightly drops compared to BLIP2, and it further drops on GQA dataset with slight improvement on OK VQA dataset. We find that the overall trend it's not very consistent. The model is not able to take advantage of the benefits of both CLIP and MAE. Next, we try early cross attention mechanism, where we introduce a new cross attention layer as shown in the brown block that takes in the MAE features as the input. So in addition to the CLIP cross attention, now we add additional cross attention for MAE at every alternate layer, thus adding like more parameters to the model compared to the concatenation approach. This also takes in like the learned queries as well as input text to learn the defined queries, which is Z prime. And we show that for early cross attention, we see good improvement on VQA V2 dataset, but the performance is still lower than BLIP2 on GQA dataset, which requires better semantic understanding. And on OK VQA dataset, we also see like marginal to similar performance. Thus, we find that it's a non-trivial problem to combine CLIP and MAE features to leverage the benefits of both approaches. So for that, to address this issue, we propose Xformer, where our aim is to achieve a more holistic understanding of the visual content to leverage the complementary strengths of MAE-ViT and CLIP-ViT. For this, we propose a bidirectional cross-attention mechanism that enriches the Qformer representation from MAE tokens, and it also enriches the MAE features by the global semantic information from Qformer by enabling interaction between multimodality representation and image representation. Now let's look into the stage 1 pre-training framework of our approach. So given an image, which is then passed to the frozen CLIP image encoder to compute CLIP embeddings, Then we randomly mask 50% of the image, which is then passed to the frozen image encoder of MAE to get MAE embeddings, along with learnable queries Z and input text, which is now passed to the Q-former as shown earlier, along with the clip features to learn the representation ZQ as shown here. Then we have a first cross attention with the MAE features and the enriched Q-former features to get enriched MAE representation M prime, which is then passed to the MAE decoder, which is also frozen, then optimized with the reconstruction loss as shown here. And then we had an additional cross attention which takes in the output of Q-former, which is the ZQ, and then also the enriched MAE representation to learn Z prime, which is optimized with image text contrastive learning that has a contrastive objective between the image and the text for the corresponding sample. And then image text matching loss, which is like a binary classification loss which says whether an image text pair match or not. And then image text generation loss, which generates the text for the given image. Now coming to the stage 2, which is the LLM alignment stage. Once we have trained XFormer in the stage 1, now we take the original image and compute MAE embeddings and CLIP embeddings, which is then along with the learn queries, which is then passed as an input to the XFormer to learn the enriched representation Z prime. To align this with the LLM representation space, we add a simple fully connected layer, which is then passed to the LLM decoder and optimized with the language modeling loss. Note that in this case, all the image encoders and the LLMs are completely frozen. The only trainable modules are like XFormer and the fully connected layer. Now let's come back to the combination of CLIP and MAE and see how our method compares with the other approaches. So on VK-V2 dataset, we show that compared to all the simple concatenation and early cross attention, our method gets a good improvement on all three datasets like VK-V2, GQA and OKVQA dataset, thus indicating that our method is effective in learning both the benefits of contrastive and MIM objectives. Now let's look into the experimental setup of our approach. For the vision encoders, we use EVA CLIP-ViT as the CLIP backbone, and for MAE we use ViT-H, and for LLM we use OPT model at 2.7 billion and 6.7 billion scale. For stage 1 pre-training, we employ the image text contrastive, image text matching, image text generation and masked image modeling loss. And for stage 2, which is the LLM alignment stage, we only have the language modeling loss. Coming to our experimental setup, for pre-training, we use 14 million image text pairs comprising of COCO, visual genome, SBU, conceptual caption 3 million and 12 million. And for evaluation, we do zero-shot evaluation on various tasks involving VQA on GQA, OKVQA and VK-V2 datasets. We also evaluate on fine-grained visual perception for the task of object counting and multi-class identification on COCO and VCR datasets. And for image captioning, we evaluate on COCO and NoCaps, and for image text retrieval, we evaluate on Flickr 30K. We also do some additional fine-grained evaluations on sugar crepe and flowers and food 101 datasets. First, we present the results for zero-shot VQA on VK-V2 dataset. On VK-V2 dataset, it has like an overall score along with like the detailed scores for open-ended answers, yes or no answers as well as number answers. We show that our model improves over BLIP2 at both scales, 2.7 billion and 6.7 billion scale across all tasks, and sometimes also matching the performance of the original BLIP2, which is trained on 130 million samples, which is 10 times the samples used for pre-training compared to ours, thus indicating that our model is effective at learning good representations. Next, we show the results on GQA and OKVQA datasets. We also show performance improvement at both scales, OPT 2.7 billion scale and OPT 6.7 billion scale. And we also show that similar trend of outperforming BLIP2 on GQA when trained with like 10x lesser dataset. On OKVQA, we get like very close performance. GQA also has structural and semantic annotations for the categories. We also do more detailed comparison between BLIP2 and ours for the structural reasoning categories, which includes like verify, query, choose, logical, and compare. And we show that our method improves consistently across all the categories except for the compare. And similarly, we also show for the semantic reasoning categories, which involves like global understanding, attribute or relation, category understanding or object understanding. And we show that our model consistently improves across all the categories in the semantic space. Next, we show some zero-shot fine-grained visual perception evaluation on tasks of object counting and multi-class identification that requires detailed visual understanding or like fine-grained visual understanding. So here we compare with CLIP-2 and show that our model significantly gets improvement on the object counting tasks on both COCO and VCR dataset. And similarly for the multi-class identification, we see like improvement compared to CLIP-2 on like using the best model. Next, we show results for zero-shot captioning and retrieval for comprehensiveness. We show that our method has competitive performance with respect to CLIP-2 with a very marginal improvement on both COCO and NoCaps dataset. We also see a similar trend for retrieval on Flickr dataset. We see that we have like marginal improvement on like the text retrieval and also on like competitive performance on the image retrieval. Next, we also do some analysis for query diversity by comparing the image queries with the text queries for our model and the CLIP-2 model. So we show here for some sample example from the COCO test dataset. As shown, the image queries are more diverse for our model compared to the CLIP-2. Next, we also do some additional fine-grained understanding evaluation on SugarPrep dataset for various aspects of object, attribute, and relation with different operations for objects and attributes. And we show that our model also improves across all the categories compared to CLIP-2. Further, we also show fine-grained understanding on flowers 102 and food 101. And we also show like on both these datasets our method outperforms CLIP-2. Thus, underlying that our model has better fine-grained understanding. Next, we show some ablation analysis. First, we show the ablation using early layer CLIP features, replacing the MAE to show that the early layer CLIP features are not sufficient enough to capture like the detailed visual representation required for the MLLM understanding. So we randomly pick like the early CLIP layer features and show that our method is the best across all the approaches. Next, we show the effect of reconstruction loss, whether we apply like reconstruction loss in both stages or whether we only apply reconstruction loss in stage 1. And we find that adding reconstruction loss in stage 1 is the best pre-training approach where we get the best performance on all 3 datasets. And additionally, we show the effect of different components by removing the different loss components, and whether we do horizontal flipping or remove the self-attention. We find that our method is gives the best performance when we include all of them on both retrieval and captioning tasks. Next, we show some qualitative evaluation. For object counting, here I am showing different examples. The first one shows different instances of the same class, and the second one shows very cluttered or like overlapping instances where our model is correctly able to identify all the instances accurately. And next, we show examples of a confusing case with the color. Here you ask like how many cups are there in the image, and we see that like both cup and the plate are blue color, and CLIP-2 predicts 3 while our model is able to rightly predict 2 as there are only 2 cups in the image. And then given like the background color matches with the color of the dog, our model is able to rightly predict the count of the dogs while CLIP-2 fails to identify. Next, we show some examples for multi-class identification, where the first image the object looks very similar to the fire hydrant, but it is not. So our model is able to identify that it's not a fire hydrant, while CLIP-2 confuses or hallucinates it for a fire hydrant. And in the next case, we show example of detailed visual understanding where the object is present in the background, not in the foreground. So our model is able to identify the objects in the background. And next, we show an example of confusing shape, where given an image of a bottle, whether the model is able to identify it as a bottle correctly or not confuse it with a baseball, our model is able to rightly identify that. Next, we show an example of the umbrella that is like very closely part of the background. Our model is able to identify that, while BLIP2 fails to identify that. In summary, we propose to leverage frozen vision encoders from contrastive and masked image modeling to capture both global and local visual representation for enhancing the vision language understanding. For this, we introduce a XFormer with dual cross-attention mechanism to bootstrap multimodal to multimodal generative learning that utilizes image text pairs without the need for curated or visual instruction data. And then we show that XFormer outperforms BLIP2 in a variety of tasks requiring visual reasoning with a robust visual comprehension. Thank you.